So for week 6, we're going to finish up looking at general concepts related to temperature, precipitation, and thinking a little bit about weather and climate. Next week, we'll move on to looking at specific landforms and finish that process through the end of the term. So, as you all know, that water is available to us in 3 different states: gas as water vapor in the atmosphere, liquid water in the oceans or lakes, and solid as ice. So the way that excess heat at the equator is transferred from one part of the planet to north and south is through the transferring of heat stored in water molecules. So in order for ice to turn from a solid to a liquid and then finally to a gas, the water molecule has to gain energy. So there has to be energy put into that molecule of water, and the energy to convert ice into water is called the latent heat of fusion. So it takes about 80 calories of heat to convert 1 gram of ice into water. So the main idea here is that to take cold water and turn it into a liquid or a gas, there has to be heat energy inherent or contained in that molecule. Now, once that happens, then that molecule of water or air vapor can be transferred. And so in order to transfer that water, you need evaporation, right? You need to take the liquid water and move it into the atmosphere. And so in order to evaporate water, you have to have 3 components. You have to have the energy necessary for evaporation. So heat energy is great. Cold areas are not going to evaporate as much as warm areas. You need water to evaporate, right? So there's not much evaporation in the desert. Not a lot of rainfall, not a lot of soil moisture, so not much evaporation. And then you need some kind of wind or current to move that atmospheric particle from one place to the other. Okay, so that energy that we called the latent heat of vaporization, or the energy that is evaporated is called the latent heat of evaporation or vaporization, and it takes about 600 calories of heat to evaporate a gram of water into the air. So that energy remains latent or potential in that molecule until at some point it begins to have condensation and form a liquid. And when this happens, that latent energy or that stored energy is released into the atmosphere as sensible heat. Sensible heat warms the surrounding air and is a source of energy to heat the atmosphere. Another source of atmospheric moisture is through transpiration of plants, and they are a huge source on the planet for adding atmospheric moisture. And the same 3 components are needed: energy, wind, and water. And it takes the same amount of energy, 600 calories, to evaporate 1 gram of water from a plant. And you still need the heat to impart that energy, and you need wind to move the parcels. Now, water in soil is a major component of the water available to plants. So plants take water up from the soil through their roots. It's evaporated or transpired through their leaf system. And so that's one of the reasons that scientists will often look at the texture of soil, or what is the water holding or soil holding capacity. And I think that the text talks about the fact that one mature oak tree can transpire as much as 100 gallons of water in a day. And so one of the problems with over depleting groundwater reservoirs is then there's not water available for plants. If there's not water available for plants, then there's not water available in the atmosphere as well. And so I found this map showing locations of groundwater depletion in the U.S. and the different aquifers that are being pumped. And it's pretty interesting when you look in the Southwest, in the Central California Valley, and even in some of these areas in Oregon and Washington, that these are groundwater resources that are being removed from dry areas. And so one of the aspects of removing groundwater is that we lower the water table so that plants that can normally, their root systems can normally reach water, the water table is lowered and plants die because they can't get water. Lowering the water table reduces the amount of water in streams and lakes, and that can have a huge impact on aquatic life. And then it also can cause the ground to subside or to sink down a little bit and cause deterioration of water quality. So, I mean, it's just very, but that's a great example of a positive feedback system. As we take more water out of the ground, there's less water available, so you need more water out of the ground. It's kind of pretty interesting. Okay, so now that we've got air or atmospheric moisture in the air, we're going to look at some of the aspects of air saturation, humidity. We touched on this a little bit earlier in the term, and let me fix that right now. And I don't know why that's bold. It's crazy. There we go. So when we talk about humidity, we're just talking about how much water is in the air, right? Absolute humidity, you hear that term a lot, and it's just the weight of the water volume per volume of air. So basically 1 cubic meter of air at the surface, let's say it has 2 grams of water in it, the absolute humidity is 2 grams per meter squared. Now, as air parcels rise into the atmosphere, they become the pressure becomes less, and it allows that parcel of air to expand. So it doubles in size. So 1 square meter would now have only 1 gram of water. So there's less moisture in that meter of air. And when we talk about specific humidity, we're looking at the weight of the water vapor for air. So just some terminology that you may see. So looking at the water, that the idea that the saturation level of water is directly related to the temperature of the water. So again, warm air can hold more water vapor. Cold air can hold less. And I saw that again this morning. In the shower, it's February, the house is a little colder. After a shower, the bathroom mirrors were completely clouded up. That doesn't happen in the summer. So just remember that as air temperature increases, more water can remain in a gaseous phase. As the temperature decreases, water molecules slow down. There's greater chance of them to condense and then come out as surface rain. So this idea of condensation, or turning water vapor into a liquid, when that happens, that latent heat again is released and converted into sensible heat. So the energy that was held in that water molecule now is available to warm up the air. Warm air tends to be much more buoyant, much more much lighter, and so that air would rise up into the atmosphere, can create more storms as it begins to cool and the rain condenses. So one of the things you need for rainfall is a condensation nuclei, and let's see if I can fix that one. Yeah, there you go. So the condensation nuclei are small particles. There's natural particles like sulfates or sea salts, ammonium salts in the atmosphere, and it gives the gas something to collect on and begin to get heavy. So you get enough water droplets on an atmospheric particle, and it begins to react to gravity and come down as rainfall. You also see a lot of natural aerosols, and they're the most common in a really clean environment. You get polluted air, however, and you can have pollution-rich clouds. This is one of the reasons we talk about acid rain as atmospheric moisture condenses onto acidic air particles. So once that air becomes saturated, then you begin to have rainfall. Now, the air can become saturated in two ways. One, you can add more moisture to the air, and so it becomes more saturated, or you can cool the air until its dew point or saturation point. And cooling the air is the most common way of creating condensation. So there's a couple ways, there's 4 ways that we're going to look at cooling the atmosphere, and all of them involve taking an air parcel and moving it up into elevation, because in general, in this lower atmospheric level, the higher you go in elevation, the less pressure, the cooler the air, and so you can have more condensation. So when air cools by being moved up into the atmosphere, it's called adiabatic cooling. As air comes down, or descending air tends to warm, called adiabatic warming. So let's look at 4 mechanisms that get air to move up. We're going to look at convective, which is that idea of molecule to molecule heating, convergent uplift, orographic uplift, and frontal uplift. And we've looked at a couple of these in previous chapters. So convective uplifts, let me remove that. There we go. So this is kind of a cute little diagram here. See if I can enlarge that a bit. Yeah. So convective uplift happens when shortwave radiation from the sun hits the surface. The molecules on the ground begin to warm. The warm ground warms the air above it. The air becomes more buoyant and begins to rise up. And as it rises up, the temperature of the air cools so that the cool air can no longer hold the moisture, and that can create rainfall. Now, we saw this when we looked at the Hadley cells over the tropics. The sun along the ITCZ heats up that oceanic and land surfaces. That air begins to rise up. When it gets up in the upper atmosphere, it cools, condenses. You have a lot of tropical rain. The second method is convergent uplift, and we looked at these in general with low pressure systems. So if you have a low pressure system, and once the Hadley cells also, once the convective system starts, then you have this whole convergent air. So it pulls air in as this air parcel is moving up. It creates a vacuum at the base, which sucks in more air. As that air rises up in the surface or up into the atmosphere, the temperature drops, clouds form, condensation happens, and you begin to get rainfall. So these 2 methods, let me go back here. The convective uplift and convergent uplift are the 2 forces that drive the major circulation along the ITCZ that start that Hadley cell. And then we talked about as these move up into the atmosphere, the rain falls out, then you get a very cold, very dry atmospheric parcel, and that was moving north and south, and then the colder it got, it began to descend along 30 degrees, 25 degrees, creating the desert area. So that was kind of that driver for the Hadley cell circulation model. The third method of getting air up into up into the atmosphere is kind of a physical process, and it's called orographic lifting. And orographic lifting happens when a parcel of air runs into a mountain, and it can't go through the mountain, it can't go around the mountain, and so it just gets pushed up the mountain as more air comes in behind it. And as that air begins to rise up in elevation, it cools, it precipitates, it rises more, it cools some more, it precipitates until that air parcel gets to the top of the mountain, and there's no moisture left in that air mass. As the air mass moves over the mountain and back down, it descends, it warms with adiabatic warming, and that air is very dry. And so this is where you get this rain shadow situation, where you have one side of a mountain or one side of an area is very moist and very wet, and the other side is desert. This is classic in when you look at the Oregon, the Willamette Valley, and then the eastern Oregon desert area. So the Cascade Mountain Range is very high. We have huge atmospheric moisture masses coming in from the Pacific at the west. The predominant movement of weather systems is from the west to the east. As those masses come in up over the coastal range, there's some precipitation, but those mountains aren't very high, so there's a lot of moisture left in those mountain ranges. They move over into the Willamette Valley, and as they move up the Cascade Range, they begin to kind of wring out as they get cooler and cooler, and that air mass is unable to hold more and more moisture. And then as that air descends over into eastern Oregon, that air can suck up any moisture that's left because it's warm air, and it's the relative humidity is very, very low, and you get these dry systems. The other method, or the last method of moving air up into the atmosphere in order to cause condensation, is called frontal lifting. And you can have, we're talking about weather fronts or air mass fronts, and you can have a warm front or a cold front. And each air mass creates different types of weather systems on the convergence where the two fronts meet. So if you have a warm front moving in over a cold front, the weather systems are going to be kind of gray, misty, gentle rains, kind of Oregon weather most of the time. We have lots of gray days, lots of mist, and that happens because you have a very low gradient, or the steepness of this warm front, because this is a very buoyant, very warm, very moisture laden air mass, moves over this dense cold mass, slides up over the top, and you get kind of gentle rain all along that weather front. The other extreme, though, is when you have a cold front advancing on a warm front. And here you have much more dramatic weather. This is what will create tornadoes. It creates what's called a squall line, SQUALL, a squall line along the front. So you have this very cold air mass moving in over the kind of gentle slope of the warm air mass, and so air is moved up very quickly, and that rising air that moves up into the upper atmosphere will create big storms. It will also create then convergent air masses, where it will pull more and more air into that weather system. Okay, so moving on to just talk a little bit about clouds. When we think about clouds, basically it's just condensation of water into ice, hail, sleet, all those different types. But I'm going to talk a little bit about ground fog, or fog, which is a ground cloud, and there's two kinds. Dew, which is just condensation on the surface. Usually air temperatures drop at night. There's moisture in that along the surface, and you get water droplets. Fog, two kinds of fog I want you to be able to talk about: advection fog and radiation fog. And fog usually forms near the ground. It's a condensation. It requires the air temperature to decrease. So advection fog forms when warm air and very moist air travels over a cool surface. So there's some horizontal movement of air in order to get advection fog. And the example in the book is San Francisco, because San Francisco has this situation along the Pacific where there's warm Pacific air gliding over the cold California water current near San Francisco, and that creates that big fog bank. Radiation fog is something we have here a lot in the valley in Oregon. So you have clear skies at night, and the surface of the earth continues to cool, and then you get that ground fog or that radiation fog when you have kind of warmer ground with cooler air on top of that. And so if you have enough moist air present near the ground, and the ground is a little warmer than the air, you can get a fog forming. When we talk about atmospheric clouds, they're usually classified by the height at which they're formed and the structure. So when we talk about the height of clouds, we talk about high clouds as cirro, medium or middle layered clouds as alto, and low clouds as stratus clouds. And then we can add, if it's a rain cloud, nimbo, or if it's a vertical created cloud, they're called cumulo. So we can have alto cirrus or alto nimbus. So they're kind of middle clouds with some rain in them. You can have cumulonimbus clouds, which is the great name for like big thunderheads, where you have very vertical, so they're rising up into the atmosphere with a lot of rainfall. So here's an example of two types of clouds. So this is just a cumulus cloud. They're the nice soft cotton puffy clouds. So as the summer air rises, there's not enough coolness up above to kind of create the big storm clouds, but they're condensing a little, and they're just kind of the happy little summer clouds. And with respect, then, when you compare that with the cumulonimbus clouds, or the big thunderhead clouds, these typically form when you have a lot of warmth, a lot of moisture, and then running into kind of a cold upper atmosphere situation. And then that brings us down to just looking at air masses in general. So you don't need to know this just specifically. I won't give you this map, but one of the things you are going to do this week is look at different extreme weather events, and I want you to be able to compare the weather event with the predominant air mass. And so they're defined basically by the source region. Just like winds, when we talk about an east wind, we're talking about wind coming from the east, or a north wind is coming from the north. When we talk about an air mass, we talk about where that air mass is coming from. So a maritime air mass would be coming from a water source or from the ocean. A continental air mass is going to come from a continental area. And so continental air masses tend to have very hot or very cold depending on the time of year. Maritime masses tend to be very warm and moist, and so kind of if you're having a lot of moisture coming from the Pacific, from a Pacific mass, but you're also colliding with a polar continental mass, you're going to have a lot of snow. And so just being able to kind of understand those different characteristics. So we're really kind of talking about general weather patterns. And so the difference between weather and climate is kind of the time frame. Weather is kind of that condition, that atmospheric condition over a few days or a few weeks. And when we think about climate, we're thinking about long-term averages, long-term studies. And so one of the things I've heard somebody say once is weather is let's see, let me see. Climate is what you plan for, but weather is what you get. So I may plan to go to Greece because generally the climate in Greece is warm in the summer, but I could hit, a really wet weather week. So that's one way to think about that. Weather can change minute to minute, hour to hour. Climate is that long-term average. So one thing, just looking at those maritime air masses and continental air masses. One of the weather systems that we have every once in a while in the Northwest is called the Pineapple Express. And the Pineapple Express is driven by the movement of the southern branch of the jet stream and this huge moisture coming in from the Hawaiian Islands and up along the coast and running into kind of the cold continental air, which will cause a warm, and it's very slow moving, so you get rain staying for a very long time and brings huge amounts of rainfall as these two air masses collide. Another weather event, I want you to be able to compare and contrast tornadoes with hurricanes. Tornadoes are incredibly intense. They're very low pressure systems. Talk about converging wind masses. They're just kind of like a vacuum sucking air up into the higher atmosphere, just violent updrafts. The very rapid forming, they move, like 22 to 35 miles an hour. The wind speed from one place to another, 22 to 33 miles per hour. The wind speed itself is up to 200 miles per hour. And they can be several hundreds of feet wide to a mile wide. And we measure these on what's called the Fujita scale from 0 to 5, where an F0 is very light damage, maybe some broken limbs, signs damage, things like that. Let's say an F3 is severe damage, roofs and walls of really well-constructed houses are removed, trains can be overturned at a 3, and an F5 is at the max, and the definition is incredible damage. Houses are leveled, swept away. Automobiles are like flying missiles. Trees, bark can be removed, and it's just kind of complete devastation. When we look at tornadoes, they have a very specific geographic location in the United States. We have had a couple in Oregon, but predominantly tornadoes happen because we have a lot of moisture along the Gulf, very warm temperatures, and so there's a lot of updraft, and then you have very cold air masses coming down from the Canadian continental air mass, and these create very violent storms. So when we compare that then, oh wait, I've got one more video. So I was just looking at, this is on average about 1,235 tornadoes each year in the United States. And so this was the annual report for 2014 showing the location of every reported tornado in the U.S. And you can see the huge spatial clustering. Right here, you see some clustering here. You see almost a linear pattern here, and very spotty as you get away from what's called Tornado Alley. Hurricanes are considered probably the most destructive storm known to humans. They develop not on the land but over water. The water needs to be very warm, about 80 degrees Fahrenheit. There's a very low pressure system, and air is sucked up in a cyclone, and then at altitudes it turns into an anticyclone above that hurricane. I think I have a typo here. I'll have to fix this and post that because they are not, I doubled that. Oh yeah. Okay, hold on. Okay, so I fixed that. So when we look at the exact how fast the winds are. Wind speeds for, like, say, a Category 1 hurricane are about 75 miles per hour. Well, that's pretty good. And a Category 5 can exceed 156 miles per hour. And hurricanes move slower than tornadoes. They form a lot slower than tornadoes. Typically, when they move over land, the roughness, the friction tend to slow hurricanes down. But that slow movement of a hurricane means that the moisture and the rain and the winds stay in one place a lot longer. So both of them are damaging. Tornadoes can jump around. They can just, show up in just seconds and be gone again. Hurricanes can travel very slowly like a huge freight train. When we look at the spatial distribution of hurricanes in the U.S., we see, again, we're related, or they are related to that warm Pacific or Gulf moisture and southern Atlantic moisture, and they run along the coastal range. Because they do slow down as they move over land, you don't see the effects inland very much. So then finally, in this section, this idea of looking at the expectations. So what's the future hold as far as climate change? So as far as hurricanes go, the scientists feel that if the planet continues to warm, if the oceans warm, we will have more active hurricane seasons, and the storms will be more powerful. And one of the things that the research shows that the number of Category 5 and 4 hurricanes has increased about 75% since 1970. So the ocean is warmer, and we are seeing bigger hurricanes. Tornadoes are a little bit of a different story. Major thunderstorms and tornadoes, they're more difficult to predict. The reading says that the because they happen in such little small isolated areas, it's really difficult to put in all of the elements that created that tornado or that thunderstorm at that spot and put that into the large scale climate models and make predictions for future events. We also don't completely understand how they're formed, so that prediction becomes difficult. But because hurricanes will often create tornadoes once they make landfall, the increase in larger, more violent hurricanes, it seems like they are creating more tornadoes as a result of that. So that's that first part. The next section of this will be a little bit less dense. I'm just going to talk about climate classifications and the project.